So we're discussing now the graph of the function f of x equals sine of x. So as we talked about wrapping the number line around the unit circle, we generated the basic picture, and I'm going to draw a little bit more extensive version of it here since I have a little bit more room. So I'm going to put my coordinate system here. I'm going to change my scale so it's a little bit smaller here. I'm going to say this is 1 and this is -1 on the y-axis. Now, if that's 1, one thing I do not want you to have you work with, if this is 1 and this is -1, when you show me your work for your graph of the sine functions or the cosine functions, when you do your graphs, if you say this is 1 thing I am not going to allow, you will not get credit for this. This is not accurate. This is, in fact, not only is it not accurate, it is misleading and it can give you some wrong ideas. If you say this is 1, then you better not put pi right here. Because if this pi is a little bit more than 3, so if this is 1 on the y-axis, there's no way this is 3 on the x-axis. And so this is what I want to ask you to do. You do not need to make it precise. You do not need to get your little calipers out. You do not need to get exact, precise precision of measuring tape. And I absolutely don't want you to get some sort of a computer-generated picture. But what you do is this. If this is 1, then just approximate it. If this is 1, then you should approximate 1, 2, 3, and a little bit more. That's pi. Because we know pi is 3.1415, so on, so on, so on. Pi is a little bit more than 3. So if this is 1, then go 1, 2, 3, and a little bit more is pi. Now, the x-axis scale and the y-axis scale are at least approximately equal. They're approximately the same. If that's pi, then just approximate. Double that is 2 pi. Triple that is 3 pi, and as many as you would care to draw. If this is pi on the positive axis, then this is about -pi. Just make them about the same distance. You don't need to get precision, but it needs to be reasonably accurate. If that's -pi, then this is approximately -2 pi. And we have seen that we need this. If this is pi over 2. This is about 3 pi over 2. How much is this? 1, 3. This is about 5 pi over 2. And this is about 7 pi over 2, as many as you would care to make. And then similarly, -pi over 2, -3 pi over 2, as many as you care to make in the negative direction. And now we're ready to draw in, and I'll use a different color here. Now we're ready to draw in the graph of the sine curve. Remember, the sine curve starts at 0. The sine curve starts at 0. And what I would do is this. The same thing that you do way back when you first drew your very first parabola. When you first drew the parabola, what happened? You plotted a few points, 0, 0, 1, 1, 2, comma. So you don't put 2 here and then put 4 here. The scale's off. So just like I want you to have a reasonable scale here, you have a reasonable scale here. 1, 2, 3, 4, 2, comma, 4. We have -1, 1, -2, 4. You plot a few points and then you play connect the dots. And the details of this we'll fix when we get to the calculus sequence. But you plot a few points, enough to get the basic idea, and then you play connect the dots. Now, what happens if the line misses the dot? Some of you have had me in class before. You know what to do if the line misses the dot. If the line misses the dot, what do? No, if the line misses the dot, just make the dot bigger. Just make a nice big dot and it'll be fine. This is supposed to be a rough approximation sketch. It's not a precise rendering of the graph. A rough approximation, so just make the dot bigger so it looks nice. So the same thing happens here. We're going to make several points here and then just play connect the dots. Some of you had instructors where they required you to plot 27 points here and 16 points in here. And then what you still end up doing is you play connect the dots. So I'm going to say just find the basic ones and connect the dots. Find the basic ones. I want this to be user-friendly. So with our sine curve, the same thing happens. 0, and then it maxes out at 1, then it comes back down to 0, then it goes to minimum at -1, then back up to 0, and then you continue the cycle. 0, 1, 0, -1, 0, 1, 0, -1, as many as you care to make. Continue. Now remember, in the negative direction, from negative, when we go at negative angles, this is -1 at -pi/2. So 0, -1, 1, 0 rather, +1 back down to 0. And then play connect the dots using this curve wave and very approximately, there's my picture. I'm going to lean very heavy on the approximate. What happens if the dot misses the curve? You make the dot bigger, make the dot bigger. And that's a rough approximation of the sine graph. It's very often called, I'm going to make this a little nicer here. It's called the sine wave. Sometimes you hear wave, right? You'll hear this phrase, sinusoidal. Sinusoidal means shaped like a sine curve. That's the basic sine curve. Now, I've stopped here at 7pi/2 because that's where my board ended. In principle, this goes without end. In principle, this goes without end. There's no boundary on either end. And so now what we can do is the same thing we do with every other function you've ever encountered. We need to talk about the domain and the range. Well, the domain consists of all the x values which you are allowed to use as input. Or the domain consists of all the x values which, if you use them, actually do produce an output. And it should be clear that there's no exception to any value on the x-axis which may be used, because no matter which value on the x-axis we select, when we wrap the number line, that point will fall on the unit circle somewhere. It will generate an angle in standard position, and that angle in standard position does have a sine value. And so, the domain consists of all the real numbers. I can write that in words, all the real numbers. A little bit of a note here. Let me go off to the side. The real numbers. What are the real numbers? I think sometimes what happens is it's a word that it's like the big words in the Russian novels. You just kind of blip over it and fake your way through. When a math instructor says the word the real numbers, we mean something very exact, very precise, very with a lot of precision. Students very often, it means kind of sort of something I'm not worried about it. So we need to fix that. That becomes a big deal. So when on this side of the camera, on this side of the desk, whenever you're in a math course and the math instructor says the real numbers, the real numbers corresponds to any number or any value on the number line. Any value that is on the number line is a real number. So 2 pi is a real number because it's on the number line. -7 is on the number line. 15.3 is on the number line. 1/4 is on the number line. Anything that's on the number line is a real number. So when we say the real numbers, what we mean is the entire number line. Or in this case, it's the entire x-axis. Another meaning, which is synonymous, all three of these mean precisely the same. This is any decimal. Any value that has a decimal representation. Does pi have a decimal representation? Yes, it's infinite, but it has a decimal representation. It's infinitely long. It's 3.141596 and blah, 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 whatever it goes on to. The square root of 2. Mash your button on your calculator, 1.41 something, something, something. Negative 18, there, negative 18.0. That's a decimal representation. It is on the number line, therefore it is a real number. Is 1/4. Is 1/4. Does it have a decimal representation? Yes, 1/4 has a decimal representation, is 0.25, and it stops. Any decimal that's on the number line, it's a real number. So when I say the domain is all the real numbers, I mean any decimal number you would ever want to pick. What about 4/9? If you represent 4/9, just put 4 divided by 9 in the calculator. It'll show you it's 0.444444 repeating. And so yes, 4/9 has a decimal representation. It is on the number line. It is a real number. So when we say the domain is all the real numbers, we are not just saying all the numbers and then you don't know what that word means. From this point forward, if you're in a math course and the instructor says the real numbers, it means the real numbers is any number on the number line. The real numbers is anything with a decimal. Anything that's a decimal is a real number. Anything that's a decimal is on the number line. Anything on the number line is a real number. Anything on the number line has a decimal representation. All three of these mean precisely the same thing. So, after that little interlude, the domain is all the real numbers. Now, we may express this in symbols a couple of different ways. Some of you probably have learned this. It's the interval notation form for the entire x-axis. This is more than fine. This is wonderful. This is spectacular. This is great. This collection of symbols means all the real numbers. For our purposes, that collection of symbols means all the real numbers. Another way to write this, and some of you may have seen this in another course, it's the one I tend to use, it's in textbooks. It'll be it's kind of a Gothic script R. It's like the R it's the first letter of the chapter in the book of fairy tales. It's always enhanced like this. So you see some really cool Gothic script R. I think there's one on Microsoft Word. Most word processors have a really nifty little Gothic script R to represent the real numbers. This is not the symbol I will do because it takes way too long. Textbooks don't. Sometimes textbooks will have a really cool Gothic script, but the way I will do it is this. And anyone who knows what you're doing knows what this means. Anyone who knows what you're doing knows what this means. If they don't recognize this symbol, then they don't really know what you're doing. If you make an R with 2 vertical strokes, that means the real numbers. If you don't have the 2 vertical strokes, it can be ambiguous. The 2 vertical stroke, the double stroke R, means the real numbers. The real numbers, the real numbers, the real numbers. Everything on the number line, everything on the number line, everything on the number line. Any decimal value, any decimal value, any decimal value. The domain of the sine curve is all the real numbers. The range, however, notice we are not using the entire y-axis. The largest possible value on the y-axis is 1. The smallest, notwithstanding my bad picture, the smallest possible value on the y-axis is -1. So the range only goes from -1 to +1. The range is the closed interval from -1 to +1. Sometimes you'll see this. Sometimes you'll see -1 is less than or equal to y is less than or equal to +1. This is much, much, much less common. This is far and away the most common. The version I will use is this. I will use this version. I will not write this unless there's some special reason to do that. As far as the domain, I will freely use this all the time. It's just all over the place. I will freely and openly use this very often, and I will freely and openly use this very often. So all 3 of these need to be in your comfort zone. You need to recognize that if you're thinking in your mind all the real numbers and you see this picture, you need to know those mean the same thing. And you need to know that if you're seeing this in your mind's eye, maybe it's a multiple choice question, and in your mind's eye, you're thinking this, but the multiple choice is this, then you need to know those mean the same thing. All right? This means the same thing as that, and that means the same thing as this, and this means the same thing as that, and that's the same thing as this. They're all the same thing. And I will use them all freely. Textbooks use them all freely. Instructors use them all freely. For the range, this is really the most standard. But for the domain, any one of those three is likely to get used. All right, so all that said, there is the basic shape sine curve. Now, when you first graph your parabola, there are a couple ways. There's two ways to do this. One way to do it is you plot some points and you try to get a reasonable amount of accuracy. That's one way, and that's important, and you know how to do that. That's what I've done here. I've actually plotted some points, and I tried to get a reasonable approximation with at least tipping my hat toward the notion of accuracy. A second way to think of the basic shape square function is this. Just what's it look like? And it looks like that. I mean, it's just kind of a rough, really basic mind's eye kind of sketch version. You need to have both of these in your skill set because sometimes just a rough picture is good enough. Sometimes a little more accuracy is required. The same thing happens here. Sometimes a little more accuracy is required, so you need to be able to do a little more accuracy version. Sometimes all you need is the basic picture. When that happens, all you need is this. You should have this in your comfort zone, just like you have this in your comfort zone. If someone says, visualize in your mind the basic shape square function, boom, there it is. If someone says, visualize in your mind the basic shape absolute value function, boom, there it is. You don't put a scale on here. You don't try to make it accurate. You just roughly visualize the picture. If someone says visualize, and not if, when someone says visualize in your mind's eye the basic sine curve looks like that. Now, if you need more accuracy, then you don't do this. If you need more accuracy, then you would do what we just did here. You would make a scale. Here's 1, here's -1. So if that's 1, 2, 3, there's about pi. There's pi over 2. And then you plot the points and you connect the dots on that picture. And so you get a little bit better picture, just like you did down here. Both of these need to be in your skill set. The ability to plot the correct points and get a little bit more accurate picture, and the ability to just say, what does the sine curve look like? It looks like that. Both of those need to be in your ability. And we're going to do this so many times, it'll happen over and over and over again. If you hang around the coursework at all, this happens over and over and over again because these are some of the most useful functions that exist. And so this will become just second nature to you, but it needs to become second nature to you.